It's a pleasure to introduce the next speaker, who's Frauenfelder from Seoul National University in Korea. And he will talk about Rabinowitz Floer homology.
Thank you very much, and thanks to the organizer for this beautiful conference. Rabinowitz Floer homology, we will abbreviate just by RFH, and so you have already heard in some of the previous talks. So that's some of the semi-infinite dimensional Morse homology associated to a Rabinowitz action functional. So what is this action functional? So let's assume we have some symplectic manifold. And assume also that the symplectic manifold is symplectically aspherical. So symplectically aspherical, meaning that omega vanishes on pi 2 of m equals 0, and let's assume that we have also given some autonomous Hamiltonian. It's just some smooth function from the manifold to the reals, autonomous Hamiltonian. And I abbreviate, I add the component of contractible loops in the free loop space. So that's a free loop space, and that's just a component of contractible loops. And then this action function, AH, goes from this loop space times R to R. And so if I give you a loop and the real number eta, then this action function AH V eta, this equals minus the area of a filling disk. So this V bar is a filling disk for V, as if this is V, and we assume that it's contractible, so we can fill it up with a disk V bar, and minus eta integral 0,1 h vt. And so first, since we are symplectically aspherical, this makes sense, it's independent of the choice how you fill up your disk. Then, so you can think of this eta as some Lagrange multiplier, and then the constraint here is given by the mean value of this Hamiltonian along your loop. So what are the critical points? So critical points, so if we differentiate first with respect to the loop, so if we differentiate the first term, so we get ETV, and if we differentiate the second term, we get minus eta, the Hamiltonian vector field of H, so this equals minus eta xh of V, where this is the Hamiltonian vector field, which is implicitly defined by the following equation. And so that if we differentiate with respect to the Lagrange multiplier, we get, of course, a constraint. So the constraint is integral 0,1 h vt dt equals 0. So this is our critical point equation. But now, since our Hamiltonian is autonomous, does not depend on time, so this h is constant along an orbit. So, and we have a point, we have a mean value constraint, so we get pointwise constraint. So that's just preservation of energy. This Hamiltonian. This equation star is equivalent to the equation star star, which is dTv equals eta xh of v, and then hvt equals 0, so pointwise. And so what is this equation? So we can think that this v corresponds to a periodic orbit on the energy hypersurface h-1 of 0, and the Lagrange multiplier just gives us the period of this periodic orbit. So the v is some periodic orbit of xh on the energy hypersurface sigma h-1 of 0. This is the energy hypersurface. And eta is the period, but this is also allowed to be 0, and it can also be negative. So in negative case, we just traverse backwards, and if it's 0, then we have just a constant point as a constant solution. We say also period in this case. So it might be maybe a bit generalized, a kind of period. So it might be 0 or negative. And now let's first look at a class of perturbations of this action functional, which I looked at with Peter Albers. So there's some perturbations of this action functional of AH that was looked at with Albers. And so we assumed that this Hamiltonian is autonomous. We can, and from that we got this condition. We deduce that h is constant along the critical point. This continues to hold if the Hamiltonian is only weakly time dependent. The weakly time dependent Hamiltonian. If we take some some smooth function from the circle to 0 infinity, which is normalized so that the integral high t dt equals 1, and then let h high, which is now time dependent Hamiltonian, is just given by h high of xt. So it depends on a very easy way. On time, it's just high t of hx, just multiplying your Hamiltonian with a time-dependent function for x in n and t in s1. So if you just replace h by h high, then critical points basically don't change. They just get reparametrized via high. So we have still, up to reparameterization, we still get these periodic orbits. So then crit a h high, they correspond to some reparametrized periodic orbits on this hypersurface sigma. But now what we can do is we can make time dependence in only 1/2 of S1, and then we have the other half free, and in this other half we can perturb. And so we perturb with an additional time dependent Hamiltonian, some additional time dependent Hamiltonian, where I abbreviate ft equals just f evaluated at t. It's not just a function on m for t in S1. And to get interesting, dynamically relevant critical points for these perturbations, I assume that f and this h chi have disjoint time support, and we call this a Moser pair. This h chi f is called a Moser pair. If ft is 0 for t 1/2 to 1, and on the other side high t is 0 for t in the other part of the interval 0 to 1/2. So we have that h high and f have different time support. H high and f have disjoint and time support. And then for such a Moser pair, then this perturbed Rabinowitz action functional this a h high, and now I take f subscript as perturbation from loop space times R to R. This is just if I again pick a loop and a Lagrange multiplier eta, then this is the old Rabinowitz action functional AH high minus this integral, the integral of f along this loop. And for this perturbation of Rabinowitz action functional, the critical points have again some dynamical interpretation. So namely, these critical points of this perturbation, they correspond, or they give rise to Levi's intersection points. Just if you have some critical point, and then you map this critical point to v of 0, or call this x. So I claim this x is a Levi's intersection point. So what is a Levi's intersection point? Namely, if x is a point on this energy hypersurface, then the leaf through x, this is just the points you can attain by using the flow of h. So this, the leaf of x, this is just phi t h x, where t is in R. And so this is phi t h, this is the flow of xh. And a Levi's intersection point this is x in sigma, such that the time 1 map of f applied to x again lies in the leaf of x. So that's pictorially, if this is our energy hypersurface and this is our point x, then we have here the leaf the leaf through X, and then we follow the flow of this other Hamiltonian, which is unrelated to H, so we might even get away from this energy hypersurface, so we will go somewhere here, but then we will come back to the same leaf of X, so that's then phi 1f of X as in the leaf. And so you might think of leaf, if you think of this f as some perturbation of your Hamiltonian system, something like some earthquake, then if there would be no earthquake, your world would just propagate along this leaf. But now this earthquake happens, but after your earthquake, your world just proceeds as if nothing happened. So the question is if such solutions exist, and this question was goes back to work of Moser, and so that's why we call this Moser pair. Now, let's do some computation of Rabinowitz Floer homology before we actually defined it. And so we will actually see that we can't define this Rabinowitz Floer homology just for general energy hypersurfaces. But so let's some computation of RFH before definition. So this computation will not make sense completely. So, but the case 1, we can tell what Rabinowitz Floer homology should be is, so assume XH has no non-trivial periodic orbits, except what you always have is constants. Eta is just 0, but assume there are no other ones. So XH has no non-trivial periodic orbits on sigma. So other periodic orbits of period different from 0, then what should Rabinowitz Floer homology be? Yeah, in this case we have just the constant solution. So the constant solution correspond just to points on the hypersurface. So we have just one critical manifold consisting of this hypersurface, and in this case Rabinowitz Floer homology should just be the homology of this critical manifold. So in this case we get RFH of sigma v. This should be just homology of sigma. And so the reason is that the critical set of AH just is diffeomorphic to sigma, so that is which corresponds to the constant periodic orbits. And now consider another case, now namely a case where this sigma is Hamiltonian displaceable. So recall that a sigma is called Hamiltonian displaceable if there exists some time-dependent Hamiltonian of compact support such that the time 1 map of F displaces sigma from itself. And so in the second case, we can tell what this Rabinowitz Floer homology should be is if sigma is Hamiltonian displaceable, then this Rabinowitz Floer homology should be just 0. And why is that? So if it's displaceable, then we have in particular, we have no leafwise intersection points. We have not even points which come somewhere back to the hypersurface. So there are no, at least for this perturbation, there are no critical points anymore. And so we want that this Rabinowitz Floer homology should be invariant under this kind of perturbations. So in this case, it's just there's no critical points. So the reason is there are no leafwise intersection points. But this does not make sense, since there are actually examples of energy hypersurfaces which have no periodic orbit, but which are displaceable. These are the counterexamples to this Hamiltonian cipher conjecture, going back to Victor, Ginzburg, and Hermann, and Burel. So the point to note is that this cannot be true in general. There are displaceable hypersurfaces with no periodic orbit, no non-trivial periodic orbit. And so-called counterexamples to this Hamiltonian cipher conjecture. So due to Hermann, Ginzburg, Burel. So if we want to define a Rabinowitz Floer homology, we have to assume some more conditions on these energy hypersurfaces. And so what's the reason, or why does it fail to define this Rabinowitz Floer homology just in full generality? So if we want to define some Morse homology, then we want to count gradient flow lines, and we need some compactness for these gradient flow lines. And otherwise, counting gradient flow lines was not give a boundary operators. We have no well-defined homology. So the upshot is we need additional assumptions on this energy hypersurface sigma, and so this corresponds to the following analytic difficulty. So we want to define a boundary operator delta by counting gradient flow lines, of AH, this Rabinowitz action functional, and the t square equals 0. This translates into some compactness properties. properties for the moduli space of gradient flow lines. So let's derive the gradient flow equation so that we see what's the problem. So what's the gradient flow equation? So I explained the action function. To get the gradient, we also need a metric so that we can define the gradient. So what's the metric on the space we are working on L times R? So we pick some smooth family of omega compatible almost complex structures, and then if we have a point v eta in L times R, and we have two tangent vectors at this point, so they live in the tangent space of v eta of L times R, whereas this tangent space, the tangent space to this loop space, these are just vector fields. Vector fields along the loop, so that's just a section from S1 to pullback bundle of Tm by V, and then so the R vector is just trivial. And then so this metric at the point v eta applied to v hat 1, eta hat 1, v hat 2, eta hat 2, this equals first the integral of v hat 1 t j t v t v hat 2 t. So this is omega compatible, so this is a time-dependent Riemannian metric on M, and then plus eta hat 1 times eta hat 2. And if we compute the gradient of Rabinowitz action function with respect to this metric at the point v eta, then what we get, so again, if we first differentiate with respect to the loop, so we get jtv dtv minus eta xh of v, and if we differentiate with respect to the Lagrange multiplier, we get, of course, again the constraint, which is this mean value of h along the loop, and therefore the gradient flow lines, so these are now v eta, but they are flowing, so loop which flows, this is, we think of as a cylinder, a map from R times S1 to M, and then we have this Lagrange multiplier which also flows, so we have a map from R to R, and they satisfy, so formally the S derivative of eta is plus the gradient is 0, so if you plug in this formula, we get dsv plus jtv dtv minus eta xh of v equals 0, and then second equation ds eta equals the mean value of h along this loop. So this is our gradient equation. And so we need some compactness statement for this kind of equation. And so there are three problems, three difficulties, how these solutions could escape. So there are three problems for compactness. Where, of course, gradient flow lines can always break, but that's okay. They do also in finite dimensions, and this gives us actually d squared equals 0. But to get compactness up to breaking of this equation star, 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 so what we need is we first have to make sure that our loop V cannot escape. So we need an infinity bound on V. Then we have to make sure that our Lagrange multiplier cannot escape. So we need an infinity bound on eta. And third, we need also to control the derivatives of V, so L infinity bound on derivatives of V. And so problem 1 and problem 3, these are some kind of standard problems in Floer homology. So 1, those are standard problems. One knows from classical Floer theory how to deal with. One follows if this symplectic manifold M omega is compact or behaves nice at infinity, which is technical term is geometrically bounded. And 3 follows since by our assumption that our standard assumption that omega vanishes on pi 2, there cannot be bubbling, and since there is no bubbling, derivatives cannot explode. And the explosion of derivatives would lead in existence of a bubble, which does not exist. So 3 is, since there is no bubbling, if omega vanishes on pi 2 of m. And so the only new ingredient is this bound on this Lagrange multiplier. So there's a bound on the Lagrange multiplier. This is peculiar to this Rabinowitz Floer homology. And so, as I indicated before, this can't work in general, since otherwise we would contradict well-known facts. Victor would get angry if he could disprove your theorem. No, so if you could bound the Lagrange multiplier always, you would get angry, since this would contradict one of your theorems. But we can't do that. So So, but as this 2 is established so far in the following cases. So that's first, if sigma is of restricted contact type. This was what I originally looked at with Kaitz-Hildebrand. And then with Gabriel, we generalize this to more so if to the case where sigma is virtually contact, or to the case where sigma is stable. Yeah, okay. The bound on the Lagrange multiplier always works, even without tables. So that's Silly-Beck and Gabriel, pattern 9. And so let me explain, say some words to the easiest case, to this restricted contact type case. So why does restricted contact type help us to get the bound on the Lagrange multiplier? To case A. So in the restricted contact type case, the m omega is exact, meaning that omega equals d lambda, and the restriction of lambda to sigma is a contact form on sigma, and then we have some arrays and the reap vector field, and let's normalize H such that the Hamiltonian vector field of H restricted to sigma is just a reap vector field. And under this normalization, then the crucial observation is that if V eta is a critical point of AH, then the action value of Rabinowitz action functional at V eta is just minus eta. So we get an asymptotic bound on the Lagrange multiplier in terms of action. And then using the gradient flow equation, we can always, this eta cannot wiggle too much around the action, but the action along the gradient flow line is just decreasing. So on the action we have very good control, and then using this action we can then actually control this Lagrange multiplier. So we have some asymptotic bound of Lagrange multiplier in terms of action. And then using gradient flow equation, gives us uniform bound on eta. And so in this case, in this restricted contact type case, so we can now define this Rabinowitz Floer homology. And so let's do some computation. So let's tell you next what we know, what it is. So the first theorem is actually, I already explained why. This is, if you can displace the hypersurface, then this Rabinowitz Floer homology just vanishes. So theorem 1, this was with Silly-Beck, is if sigma is displaceable, then this Rabinowitz Floer homology vanishes. And then the second theorem, this is joined with Alexandru Vancea. And for the second theorem, there is now also independent other proof of Alberto and Matthias. So this is in the case where we have some, let's assume as LG is some closed Riemannian manifold, and SL, this is the unit tangent or cotangent bundle. We have a Riemannian metric, so we identify tangent cotangent bundle. So SL, these are the tangent vectors such that of length 1 in the tangent bundle identify the cotangent bundle. This is unit tangent bundle. And LL is now in the loop space of L is the component of contractible loops in L, and then the result is DM2. So this was again with Silibeck and Alexandru, and independently by Abondandolo Schwarz. So we get that this Rabinowitz Floer homology is basically two copies of the loop space homology of L. So there's two copies, since we have also these negative traversed loops. So we have also entries in negative degrees, and so the precise formula is that for the unit tangent bundle in the tangent bundle, this Rabinowitz Floer homology, this equals the loop space homology if star is bigger 1. It equals the -1 plus 1, the cohomology of the loop space if star is less than 0. And in low degrees, it depends a bit on the Euler number. It equals H0 of the loop space plus H first cohomology group of the loop space in degree 0 if the Euler class of TL is 0, and if the Euler class is different from 0, it equals H1 of L. So this is in degree 0 if Euler class is different from 0, and then in degree 1 it equals H1 of LL plus 0's cohomology of the loop space in degree 1 if Euler class is 0, and it equals H1 of LL in degree 1 if the Euler class is different from 0. And so we prove this using some long exact sequence which relates this Rabinowitz Floer homology to symplectic homology and homology, and then we used another result which is goes back to Viterbo and then was proved by Salomon Weber and again Abonandolo Schwarz, which relates symplectic homology to this loop space homology. And now there is a new proof which directly relates Rabinowitz Floer homology to this loop space homology. So as the corollary of this theorem 2, so we can deduce, so the loop space homology is very rich in this, in the case where if L is simply connected, then this is infinite dimensional. This is due to the theorem by Figuier-Perrier, Sullivan and Figuier-Perrier. So this is infinite dimensional, and so in particular we get infinitely many leaf-phase intersection points, at least generically. So a corollary is that assume L simply connected, and then generically infinitely many leaf-phase intersection points exist. Yeah, okay. So if it's not simply connected, then you can look in all classes. Yeah. So there is I think there is, so pi 0 of the loop space are free, the free homotopic classes of loops. And so this, so even if the fundamental group is infinite, there could be only finitely many free homotopic classes.
With infinite fundamental group and finitely many ambiguous for sure.
Finitely percent, right?
Yeah, sorry, finitely percent.
Finitely generated.
Finitely generated, infinite, and finitely many.
Okay, so if you have finitely many,
Right. So
free
assume you have infinitely many free free homotopic classes, then you can also get it just by looking at different components. And that is actually true always, not generically, since they are homotopic class distinguish them. So there are infinitely many leaf-phase intersection points for SL in TL, and so then another question is, so we don't know in general if this Rabinowitz Floer homology actually depends on the filling. It might be conceivable, but I actually don't think that this is true, that it only depends on this contact, this boundary. And so we have no example where it depends on the filling, but we can in some examples we can tell that it does not depend under some assumptions. So let's say as open question, does Rabinowitz Floer homology depend on the filling? And so partial answer this was again with Alexandru. So theorem 3, Sillibeck and Wancha. So assume following conditions. first assume that C1 of M also vanishes on pi 2. And secondly, for simplicity, let us assume that the boundary of M is simply connected. Or otherwise, you could assume that the pi1 injects into the filling. And third, assume that there exists contact form lambda on M such that the condescender index of gamma is bigger 3 minus n for all contractive or for all real orbits on EM, where n is half the dimension of the symplectic manifold. And under this condition, then this Rabinowitz Floer homology is independent of the filling. And so just how does this strange condition appear? So this theorem is based on a compactness result from symplectic field theory, and this condition is some well-known condition in symplectic field theory. It excludes existence of holomorphic planes, and that's why it appears also here. And so we can we get as a corollary, as a further corollary of all the 3 previous theorems, we get obstructions to exact contact embeddings. And then assume that L is a closed, simply connected n-dimensional manifold, and if L admits a Riemannian metric G such that the Morse index, which corresponds to this condescender index, so the Morse index is bigger 3 minus n for every closed geodesic C, then the unit tangent bundle of n admits no exact contact embedding into subcritical Stein. Manifold, or so why is that? So if it admits exact contact embedding, so by this theorem 3, it does not depend on the filling, so we can just take as filling the cotangent bundle itself, but then we know that Rabinowitz Floer homology is different from 0, and if in subcritical Stein it would be displaceable, so it had to vanish. So that's, here I stop. Thank you very much.
Are there questions?
Yes.
Is genericity, is it essential or do you have
Yeah. So there is the following thing. So if critical points of Rabinowitz action function would give rise to Levi's intersection points. But now it could happen the following. So you could have some periodic leaf. And then you have some Levi's intersection point on a periodic leaf. Something like that. And then the Rabinowitz Floer homology sees infinitely many critical points. Since this is one, but you can also go here several times around. So it sees infinitely many critical points. This does not appear generically. But if it appears, then
so this should be covered in this different
this is only one Levi's intersection point, but this gives rise to infinitely many critical points.
Yeah,
Right.
but in addition to that, I mean, there are sort of transversality conditions, right?
Yes, that's okay. That's
Which would, hypothetically at least, it's like the difference between Morse theory and the Stern-Schneermann theory.
yeah. So actually, we are working on that to remove this. So there should be always
This problem you won't be able to
no
do.
this problem this
You will do this, you will do infinitely many judges.
right. So this problem no, but at least to show that always we have infinitely many critical points, even without Morse. And so this should be possible.
More questions? Comments? So let's thank Urs again. And information about this afternoon, we will have a bus leaving here at 2 going to